This is a video tutorial for the fluid. We'll be going through the theory and motivation behind the experiment before showing the equipment you'll be using and how to use it. We'll then briefly outline the calculations and analysis required for your submission. The aim of this experiment is to verify Bernoulli's principle. This is an important law of fluid dynamics that states that for horizontal, frictionless fluid flow, the sum of the pressure energy and the kinetic energy is a constant. This therefore gives us a relationship between the velocity u and the static pressure P, such that if we increase the fluid velocity, the pressure must decrease to satisfy this expression being constant. This can be rewritten in terms of pressure, such that the static pressure P plus the dynamic pressure, which is related to the kinetic energy, is equal to the total pressure. Now, considering the total pressure to be a constant, we have a similar relationship between the static pressure and the velocity, such that an increase in speed will lead to a lower pressure, a decrease in speed, a higher pressure. In this experiment, you'll be verifying this relationship. The equipment you'll be using for the experiment consists of a Venturi tube, through which the fluid flows at varying speed, and above this, manometers that you will use to monitor the static pressure. A Venturi tube starts at a given cross-sectional area, converges to a smaller cross-sectional area, and then diverges back out, in this case to its original size. With a constant volume flow rate, the fluid will start at a given velocity, get faster as the tube gets smaller, and then slow down as the tube gets larger again. So according to Bernoulli's principle, as this occurs, the static pressure should decrease to a minimum where the fluid is fastest, and increase back up to its original value at the end of the tube. So to verify Bernoulli's principle, you will need to measure the fluid velocity and the static pressure throughout the tube. When you arrive at the lab, the equipment will already be set up by the demonstrators, so do not turn the valves or this will affect your results and you may need to repeat the experiment. You won't be measuring the fluid velocity directly, but rather measuring the volume flow rate and calculating the velocity based on the tube dimensions. The Venturi tube has well-defined cross-sectional areas. By measuring the volume flow rate, that is the volume flowing through the system per unit time, and dividing it by the cross-sectional areas at each point, we can get a corresponding average fluid velocity at each point. In this experiment, you'll be using a measuring jug to collect water as it exits the tube, and a stopwatch to measure the time this volume of water takes to flow. Place the jug on a level surface and wait for the movement to stop before taking the reading. By dividing the volume by time, we have volume flow rate. Repeat this until you have 5 values of flow rate that you can average in your analysis. Also make a note of the resolution of each of the scales you're using. That is the smallest increment on the scale of the jug and stopwatch, and consider sources of uncertainty that may affect the accuracy of your data. In order to measure the static pressure, you will use the manometers that are positioned at various points along the tube. By reading the height of the water in the manometer, in other words the pressure head, you can calculate the static pressure by multiplying it by the fluid density and gravitational acceleration. These measurements should also be taken 5 times for averaging. Again, make a note of the manometer resolution and any sources of uncertainty. If Bernoulli's principle is correct, we can expect the static pressure to decrease as the fluid speeds up, and then the pressure to increase back again to its initial value as the fluid slows down back to its initial speed. Once you've collected the necessary data, you will be able to carry out the analysis required on the lab script, which is available on Blackboard. You will have to use your experimental data and the equations provided to calculate static pressures, volume flow rate, and fluid velocities at each section of the tube. You will then have to compare this experimental data to what Bernoulli's principle predicts. In order to do this, you must calculate the total pressure by plugging in the initial velocity and initial static pressure from manometer 1 into the Bernoulli pressure equation. Then, use a rearranged Bernoulli equation provided to calculate theoretical pressures based on the velocities you will have already calculated. The lab script will provide you with instructions and equations for your answers. By plotting the experimental and theoretical pressures on a graph, you can then compare any differences between them. These differences should be described in the discussion section and the reasons for them explained clearly. You will also be asked to discuss sources of uncertainty that may have affected your measurements. Further information and details will be given by the demonstrator in the lab session, and attendance is required, or no marks will be given for this part of the module.